Hi, so today we're going to be looking at a problem on classical mechanics. And well, today we're going to be using the Lagrangian formalism, and in other videos we will use Newtonian, Hamiltonian, or even Hamilton-Jacobi formalism. So let's get on with a quick recap, and we'll get on with the problem then. First of all, we need to determine the equations of motion of our particle or system of particles. So these are the Euler-Lagrange equations, which are in terms of the Lagrangian, which is just the kinetic energy minus potential energy. Okay, this is the name I'm giving to kinetic and potential energies. And it is just the partial with respect to Q, which is the generalized coordinate. We'll see later on what a generalized coordinate is, minus the time derivative of L with respect to Q dot. And Q dot is just notation, usual physics notation for time derivative of Q. This substrate I going from 1 to n just depends on the number of generalized coordinates that we have and the number of equations of motion that we need, okay? So we'll see later on how many we need in our case and how they are related to the number of generalized coordinates. Now the kinetic energy can have two components, okay, let's in our problem it will have two components. One is linear, due to linear velocity, 1/2 times mv squared, where I'm using this notation. V squared is just the dot product of v with itself, which is really just the modulus of the vector squared. And if you remember, v is just the time derivative of our position vector. Now, this is the analogous to the kinetic energy due to rotation, and it's 1/2 times the moment of inertia times omega squared. Angular frequency, omega, and moment of inertia is analogous to the mass, but whereas the mass refers to the resistance to a change in momentum, or linear momentum, the moment of inertia is a measure of the resistance to a change in the rotation of our body. We will go into more depth in these concepts in other videos, but for now, let's just consider these results and get on with it. Now, the moment of inertia of a disk, or even a cylinder, it doesn't matter, is just 1/2 times m times r squared. Of course, if the disk is rotating around this central axis, okay? If it was rotating around another axis, then this moment of inertia will change. And we'll see in other videos how to compute this one and how to compute it with respect to other axes. And now the potential energy, well, we can define it as the difference in potential energy between the position of our particle and some reference position, which I will call R0, and we'll see later on how we will choose it and what all of this will turn into. And in our case, yeah, I don't know if I said it, I don't remember, we're just going to be considering the gravitational potential energy. And yes, the reason that I wrote this just means the y component of our position vector, is that we're considering that gravity is going in the minus y direction. So we will need the y component of our position vector. We'll see later how this all works. Now the harmonic oscillator, it's a really important body in system, really important system in physics. And it's so important because really a lot, if not all, systems can be modeled with a harmonic oscillator. Because it is a simple system which we can solve. We know the analytic solution to this differential equation. Okay, this differential equation just means that we have a harmonic oscillator if the system satisfies this equation. So we can model a lot of systems with some approximations, some assumptions by harmonic oscillators, either in 1 dimension, 2, 3 dimensions, or even in higher dimensions. And this t is just the period, which is 2 pi over the angular frequency. And this angular frequency is the angular frequency of our harmonic oscillator. We'll see later on how it is. But really, you can just think of it as a mathematical system which is described by, or a mathematical equation that is just the double time derivative being equal to minus some constant squared times x. Well, this minus constant squared means that this is in general negative, because this should be or we are considering that omega is a real number squared is positive, and this minus sign makes this negative, okay? So, and the general solution we'll see later on, but in general, the general solution is just some constant times the cosine omega t plus b sine omega t. And we'll see how to compute this solution, but not today, in other videos. What else? These conservation laws. This right here is an important parameter or quantity in Lagrangian and Hamiltonian mechanics and Hamilton-Jacobi, which is called the energy integral. It is not the energy, except in some specific cases. But in general, you just have to account that this is not the energy, although it is called the energy integral. And it's just the sum of the time derivative of the generalized coordinate q times the canonical momentum p minus the Lagrangian. The canonical momentum is defined as, well, this term right here, partial of L respect to q dot. And what we care about this today is that, well, if the Lagrangian is independent of time explicitly, right, partial derivative is 0 with respect to time, we get that this energy integral is constant. This is the first conservation law that we'll be seeing today. And if q is a cyclic variable, what is a cyclic variable? Well, a cyclic variable is just a variable or a generalized coordinate q, or cyclic coordinate, okay, which satisfies this. Or let me just put a subscript I, that the partial derivative of L with respect to q is 0. It is called cyclic because it doesn't really affect our Lagrangian, and thus it doesn't really affect our equations of motion. So if this holds, then the canonical momentum, which is just partial with respect to q dot, is conserved, is constant. So I think this is quite a fast recap. I will be making videos in which we'll go into more depth about Lagrangian, Hamiltonian, Newtonian, in Hamilton-Jacobi mechanics. But for now, let's just take this for granted and try to understand how to apply it. Because I think in many cases it's better to kind of see a little bit of the theory first, recap, do a lot of exercises, learn how to mechanically do our exercises and how to understand them, and then go into the theory and try to understand it really well. But well, let's just get on with the problem. Okay, we have a disk like this, which is rotating with respect to this central axis. Okay, I will not be drawing it, but it's rotating like this with angular frequency omega. And the thing with this disk is that, well, really it is just rolling, not just rotating. That is, if this is the ground, which I'm going to call x-axis, this disk is rotating. So it is rotating and advancing at the same time. Let's just call this the center. And let me just call this Cm, center of mass of the disk. And apart from that, we get some particle with mass m, and this connected to the center of the disk by some rod of length v. And what else? Well, we know that the radius of this disk is a, and its mass is capital M. What do we actually want to do with this? We want to determine the motion of M. We want to see as time passes, depending on where this mass is, or how this angular frequency, how big or small it is, how this mass is going to be moving. Of course, from intuition we can say that it is moving like this, but with this rolling disk advancing, the motion will change quite a bit. So we'll see how this motion is actually. And as always, we will just put some arbitrary reference frame, and the most comfortable one is just to consider x as being the ground and y being actually anywhere. From this, what I like to do always is to determine the position vector of the particle. So let's just say the position vector, and we will call the position vector of this particle, which is just this vector right here, Rm. But how do we describe this mass in terms of the things that we know? Well, we can do two things. The easiest thing we can actually do various things, but the easiest thing I think is to choose two coordinates and then describe m. And the two most natural coordinates in this case are, well, this angle right here, which is going to be describing how this mass is moving with respect to the Cm, and the position of the Cm. Right? If we know the motion of this valve with respect to this, we only need to determine the position of this point, which will be like our near origin. I hope this is clear, but if not, you'll see how this goes. So I have this coordinate, theta, which is varying, okay, this particle is moving, and I have another coordinate, x, which is the x position of the center of mass, which is also varying because the disk is moving. All the rest of the things are actually constant. A is just the radius, doesn't change. B also doesn't change. So we actually just need x and theta to describe the position of m. But how do we do it? It's not obvious to describe this vector in terms of these two generalized coordinates. These are our generalized coordinates immediately. So what I like to do is to consider some two easier vectors. For example, let's first determine the position of the center of mass. Well, what is the position of the center of mass? Well, the position of the center of mass in this coordinate system is just, well, of course, x, which was, that's how we have defined our first generalized coordinate in the I hat direction, which is just the x direction, plus, well, we have to go x, and then we have to go up. How much do we have to go up? Well, it's just the radius of the disk, so this distance is just a, and a j. We can just write this as x and a, taking into account that this is our system, okay? And okay, but how do we get to m? Well, we can first go here, and then we can go from here to here. But how do we describe this vector? Let me just call it RV. Well, RV starts here. So if we start here, we have to kind of go this much down and this much to our right. So we will have to go to our right some amount, which we'll determine later, and we have to move in the y direction some other amount, okay, with respect to this point. So how do we do it? Well, first of all, what is this distance right here? Well, we have a right angle triangle. So this, we know that the sine of theta is this distance, which I'm going to be calling, well, I don't know, d. So we know that the sine of theta is d times over b. So this distance is really b times the sine of theta. Okay, this seems logical. Okay, we're moving this distance, b sine theta, to the right. So this is what we are doing. And we are also moving some distance down. If we're moving down, this just means that we need to put a negative sign, because this hat in general just goes upwards, but with the minus sign it will go downwards. And how much are we going down? Well, just like before, we are going down by this. We know that the cosine is just, let's just call this e. It is just e times over v. So this distance is b times the cosine of theta. Okay, this is just basic trigonometry. And this will be b times the cosine of theta. So if you're kind of confused why, in this case, I'm not taking the origin as the center, it's just because this one starts, we can think of it as this vector is described by how much I'm going to the right, or how much I'm moving up, I'm moving x to the right and a up, and this one is described from this position, how much I'm going down and how much I'm going right. Okay? So then, from vector addition, okay, this vector goes here, we know that this plus this gives us this, that is, that Rm is equal to Rb times plus Rcm. So if we add these two vectors, we will get the position of our mass, which is what we are trying to look for. So we'll have x plus b sine theta plus A minus, in this case, B cosine theta. A minus B cosine theta. And this would be our position vector. And now I know that you might want to have this drawing here. So I will erase this and try to rewrite it up here. But for now, really, we are not going to be needing this drawing anymore. It's useful not to determine the position vector, but from now on, all we're going to be doing is analytical stuff. So I'm just going to erase all of this. Okay, just have this in the front. I'm going to erase all of this, put it a bit smaller here, and put our results there, and we'll get on with the actual analytical part of our problem. Okay, so I wrote everything. This is our drawing. This is our position vector. I hope you can see it well. Well, these two are the two vectors that we have used to determine our position vector. And what's next? Well, usually what we have to do after we determine the position vector, we have to calculate the energy. So what is the kinetic energy? Well, the kinetic energy is actually the sum. It's just the kinetic energy of the disk plus the kinetic energy of our mass, right? Okay, this mass is right here. Because really we are dealing with this system that is both of these objects are together. So our disk, it does have some linear energy, linear kinetic energy, and some rotational energy. So we have T linear of the disk plus T rotational of the disk plus simply T linear of the mass, because the mass is not rotating. And really consider, the mass is not rotating, so its angular, frequency will be 0. So what is this? Well, the linear velocity of the disk, it's actually determined by the linear velocity of the center of mass, because all the disks are actually moving with the same velocity. So if the disk is moving with this velocity, with the velocity of the disk, it's just the velocity of the center of mass. So T linear d is 1/2 times capital M, the mass of the disk, times the velocity of the disk squared. Or what is the velocity of the disk? Well, it's just the velocity of the center of mass that we said, the linear velocity. But hey, we know that this is equal to xa. So our velocity is just taking the time derivative. And what you have to realize is that we're using these generalized coordinates. X, which is a function of time, and theta, which is a function of time too. Okay? The rest of the things are actually constant in time. So when we take the derivative with respect to time, which is the derivative of a component, having in mind that the vectors of our coordinate system are constant, the basic vectors, we get x dot and 0, because this is constant. So if we take the dot product with itself, we can just put this square here and take the product with itself. We get x dot squared. Okay, so this energy is actually pretty easy, it's just this. Now, what is the rotational kinetic energy? Well, the rotational kinetic energy of D is 1/2 times its mass, its moment of inertia, times its angular velocity. We know the angular velocity is squared. But we will just rewrite the center of mass, the moment of inertia, as this, 1/2 times mass times the radius squared. So it's 1/2 times the total mass times a squared. We call A the radius. Simplifying this, we get 1/4 ma squared, omega squared. So we get 1/4 ma squared, omega squared. 1/4, sorry. Yes. Let's check. Yes. So this will be the total kinetic energy corresponding to the disk. But what is the total kinetic energy of our mass? Well, it is just T ln mass is 1/2 times the mass of the, times our mass, or little mass, times its velocity squared. But we know that we can just rewrite this as this. So taking the time derivative of r, we get m, and this is just, x is not constant in time, so we take derivative, plus b times the derivative of the sine is the cosine, but by the chain rule, we have to multiply by this too. Now the derivative of the other component, a is constant, it's just 0. We get b minus b times derivative of the cosine is minus the sine times this theta dot again. So really, we have that these two minus signs cancel out, and we get b theta dot sine theta. And the modulus squared of this is just this squared plus this squared. So we can just write x plus b cosine theta dot squared plus b theta dot sine theta squared. This might seem like a long expression, but actually if we expand it, we can simplify a lot of things. So let me just expand this. So we have 1/2, and we get x dot squared plus 2 x dot b theta dot cosine theta plus b squared theta squared cosine squared of theta. And now we square this, it's just b squared theta squared sine squared. But we know that if we factor out, sorry, this should be a square. That if we factor out b times theta dot all squared, we get the cosine plus the sine squared, which is just 1 by the fundamental identity of trigonometry. So we get that this is actually, let me just write it here. This is actually just 1/2 times our mass times x dot squared plus this term right here plus b, let me just factor this out so you can see it clearly. This is 1 fundamental relation of trigonometry, and we get b squared plus theta dot squared. So this would be actually our total kinetic energy. We only have to add all of this up. And actually I'm going to write this here because we might need it in the future. So this is the velocity of our particle. And I'm going to write the kinetic energy up here, which is just the sum of all of this. But before, let's just try to simplify it. Okay, so remember that the kinetic energy is just the sum of these three terms. So let's see how we can simplify this expression. So we get that T is 1/2 m like this plus 1/4 m a squared omega squared plus 1/2 m. I'm going to distribute this one, a squared, plus 1/2 times the rest. Now, notice that we have this x squared factor here, so we can add these two, and we get 1/2 times capital N plus M times this. Okay, I have just put together these two terms. Plus, I'm actually going to leave this term the last because it is a constant, and as we will see later, it's not really gonna matter in our Lagrangian. So, a squared omega squared, and this 1/2, we can just distribute it here, and we get x dot theta dot b cosine of theta plus 1/2 b squared theta dot squared plus this term. Yes. Okay, so this is a kind of a simpler expression. Not too simple, but also not too complicated. So I'm gonna rewrite it up here, and we'll continue with the potential energy. Okay, so before we continue, let's just consider one thing. We have kind of assumed that this omega is constant, but let's say that it's the same. Okay, we know that the velocity of a center of mass is the radius a times omega. Okay, so what if it isn't really constant? What we do is that, well, we can rewrite this like this, and well, where this is the modulus of everything, so we will have 1 over a, and the velocity of the center of mass is just the time derivative of this, as we said before. Sorry, this is 0, and the modulus of this is just really x dot. So we can write here just x dot, and we will get x dot over a. So we can express this instead of in terms of omega, we can express it in terms of our generalized coordinate x. And because this is squared, we have x dot over a squared. This a cancels out with this a, and we get 1/4 x squared. And now, notice this. We have 1/2 here x squared and 1/4 mx squared. So 1/2 mx squared plus 1/4 mx squared is just 3/4 of mx squared. So we can either leave it like this, with this term right here, or we can include this up here. I will for now leave it like this, but just have to know that we can organize it in another way and kind of include this here and then separate this. But okay, it's just however you want to do it, however it's more comfortable for you. Now, let's get on with the potential energy. The potential energy really, because the disk is a height, or a constant height, above the x-axis, doesn't really have some gravitational energy. We're assuming that it is always on the ground, so its potential energy is 0. But the disk, the mass does have some potential energy because it is at some height above the x-axis. Okay. So how do we determine it? Well, we can say that the potential energy, or reference potential energy, is going to be the potential energy when y is equal to 0. Okay, that is the potential energy for this region right here, and we're going to define it as being 0. We're going to just say that it is 0. Then, if we have some particle here at some height h, okay, it includes the negative sign, some height h, we'll have that the total potential is potential h minus this initial potential. But this initial potential, we say that it is 0. So we're taking everything with respect to y equals 0. What does this mean? This just means that we are measuring the y component, okay, the height of our particle with respect to this x-axis. Then we can apply this. That this is just the y component of r, because r is actually measured with respect to this x-axis too. Okay? So having this into account, we get that this is just mg and the y component of our position vector. But what is the y component? Well, it is just this one, a minus b cosine. A minus b, the cosine of theta. And this would be our potential energy. Okay? So let me just write it here. Okay, so now that we have determined our position vector, velocity vector, our generalized coordinates, and our kinetic and potential energy, we can actually get on with the analytical part. by first of all determining the Lagrangian of our system. The Lagrangian is just this minus this. So I'm going to write it here. I'm going to write L is just t minus v. So we can write 1/2 capital M plus M, or maybe grouping, as we said before, grouping this term and this term, we get 3/4 of capital M plus 1/2 of M, all of this times x squared. Okay, just do it by yourself if you're not to show how this, just grouping these two terms, plus x dot, theta dot, the cosine of theta, oh, on b, don't forget the v, plus 1/2 b squared theta squared minus our potential energy, minus mg a minus b, the cosine of theta. This is the Lagrangian of our system. And from it, we can determine the equations of motion. How do we do it? Well, notice, as I said before, that we're going to need various equations of motion depending on our generalized coordinates. So we're going to need how the x-coordinate is going to move and how the theta coordinate is going to move. So first of all, let's start with how the x-coordinate is going to move. So to determine it, we need to determine the partial with respect to qi. But what is qi? Our q1, for example, is x, and our q2 is theta. These are our generalized coordinates, okay? X and theta. So, well, we have that the partial of L with respect to q1, which is x, is just 0. There's no x involved in this Lagrangian explicitly, so it is just 0. But notice that, hey, the partial derivative with respect to some coordinate qi, in this case x, is 0, so it's related. Canonical momentum px, which is just this, is constant. And when we say constant, we mean constant with respect to time derivatives. Okay? So this is going to be constant. And we can in fact check it. We can say, okay, the partial derivative with respect to x dot is, well, this, there is an x dot, so it is just this 2 comes here, and it makes all this twice as big, so we get this times x dot. Here we just get the same theta dot, the cosine of theta, b, and there's no more x dot, so this would be the partial with respect to x dot. So we have this, we have this, we know that this is constant, okay, and we are actually going to see it from the equations of motion. So, well, let's just determine the equation of motion, okay, it is this, which is 0 minus the total time derivative of this, which we know is this, so the total time derivative of all of this. And this has to be 0. But wait a minute. Well, we can just multiply by minus sign minus 1 on both sides. Wait a minute. The derivative of this is 0. That's the definition of being constant. So, hey, all of this is a constant of motion. That is, it's time. It is constant in time, which is what we saw before from the conservation law. Okay, so this makes sense. So the only equation, the equation of motion in general for our x coordinate is just all of this being equal to 0, or all of this being equal to some constant. And yeah, so this will be our first equation of motion. And I'm going to actually just rewrite it here. What this means is that all of this is constant in time, okay? It is just a real number. we could also just take the derivative on both sides and get that the root of this is 0. So this would be our first equation of motion. And our canonical momentum, px, would just be constant. And actually, let me just write it like this. Because we know that this, all of this, is just a partial with respect to x naught, which is just px, canonical momentum. So I hope that the explanations are clear. Well, I'm doing the best as I can. Now, if you think that the videos are too slow or something, just tell me that. I kind of want to explain everything very clearly so we don't get lost in some steps. But anyway, you can actually just skip to some parts, press twice velocity or whatever. I know the videos are quite long, but well, that's just how it is. If you want to explain it quickly, I could do it in 10 minutes. I mean, just put all the equations and write it fast, but I like to explain it kind of slowly and thoroughly. At least I think that's what I am trying to do. Now, we have determined the equation of motion for this first coordinate. Okay, notice that it depends also on theta, but we're not going to care about that now. And we need to determine the equation of motion for our theta, or the generalized coordinate. So, how do we do it? It's just the same as before. We take the partial with respect to theta, and what is it? There's no theta here, it's 0. There is a theta here, okay? Don't get confused. This theta dot is like a constant. We'll take the partial with respect to theta. There's one here, okay? So let's leave that for now. This is 0. There's no theta explicitly, just theta dot, which is not theta exactly, okay? So we don't care about it. And here, MGA 0 and plus MGAB cosine, okay? So we are taking the partial derivative with respect to theta of all these terms that I said before. This one, and this one, which don't depend on theta, plus x dot b theta dot times the cosine of theta, plus, okay, minus, plus mgb times the cosine of theta. As we said, this does not depend explicitly on theta. This is just this, and this. So this is 0. And notice that both of these terms depend on the cosine, so we can actually factor them out, and we get x dot b theta dot plus mgb times the partial with respect to theta. These are constants with respect to this operator, so we don't care, and we get the cosine. And this is just minus x dot theta dot b plus mgb, the sine of theta. So this would be the first part of our Euler-Lagrange equation for theta. Okay. So let me just write it here. Now, what is the other thing that we have to compute? Well, we have this. So we have to calculate the canonical momentum. That is, we have to calculate p theta, which is partial with respect to theta dot in this case. Is there any theta dot here? No, so this is going to be 0, the partial derivative. Is there any theta dot here? Yeah, this one. If we take the partial, well, everything is just a constant, and we get x dot b, the cosine of theta, okay, plus there's another theta here, so this 2 comes forward, 1/2 goes away, b squared theta dot, and there's no theta here, no theta dot, so this will be our canonical momentum in theta. Now I just want you to have one thing to have. Notice that before, when we took the time derivative, we did use the chain rule, right? When we took, for example, the time derivative of the cosine of theta is Well, the chain rule, the time derivative of this, sorry, the derivative with respect to theta of this minus the sine, but we have to multiply by the time derivative of the function inside. Yes, that's actually correct. But what if we are taking it with respect to theta? Then the thing changes, because really this theta is a function of time. Okay, so we have to use the chain rule. But when we are taking the partial or total derivative with respect to theta, or the cosine, theta is just theta. Or we can even use the chain rule. In fact, just use the chain rule, and here you will get the partial derivative of the inside function with respect to the thing that we're taking the derivative with, theta. This is just 1. So we don't get this extra factor. If you're confused about it, just practice a bit or ask me or whatever. I'll be uploading videos actually talking about partial differentiation and total differentiation. But well, this is what we have. Now we have to take the total derivative with respect to time of this. So if we take the total time derivative of this, we get, okay, the chain rule, sorry, the product rule, we get x double dot times b cosine plus x dot b times this derivative with respect to time. So this derivative with respect to time is just the one that we before minus the sine of theta times theta dot plus the total time derivative of this is just b squared theta double dot, two derivatives. And now the equation of motion is really easy to determine. It's just this minus this being equal to 0. Or if we reorganize this, put this part here, it's just making this term equal to this term. Okay? So, yeah, let me just write it up here. Now, notice that we can actually simplify this term, because this is just minus x dot theta dot b times the sine equal to this term minus mgb times the sine. We have this term xb theta dot sine with minus sign on both sides, so these two cancel out, and we end up with a somewhat easier expression, which is b squared theta double dot, okay, this term right here, plus b cosine theta x double dot being equal to minus mgb, the sine of theta. This will be our equation of motion, much simpler than what we had before, right? Now, what I'm going to do is I'm going to write it down here, and we are going to see actually how to get rid of this x double dot. Okay, so I'm going to write it here, and we'll go back to this. Okay, so now what we have so far is well, we have our Lagrangian, and from our Lagrangian we have been able to obtain the equation of motion for x and the equation of motion for theta. We can actually combine, in this case, not always, it's not always possible, but in this case we can combine both of these equations into one single equation for theta and solve for theta. But we're not going to be solving it exactly analytically. We will be solving it analytically, but we'll have to make some approximation, and that is where the harmonic oscillator comes in, the favorite tool of engineers, physicists, and in general people trying to solve some differential equations and trying to obtain some physical or some meaning from it. Okay? But well, let's just do it. How do we do it? Well, from this equation, if we take the time derivative, we see that it is 0. It's just what we did before, right? This part right here for x that we erased. So what we're going to do is to take the time derivative on both sides of this equation. So the time derivative on this first side, okay, the time derivative of this is just, well, 3 halves capital M plus M x double dot plus the time derivative of this. And I'm going to write it, in this case, explicitly. the time derivative of theta dot, the cosine of theta. And this is equal to the time derivative of what we call px, but this is just a constant. So the time derivative of a constant is 0. As we said before, from this conservation law, we had that it is actually going to be 0. Sorry, constant. Constant. When you take the time derivative, it is 0. So if we apply the chain rule here, the product rule, I always get confused with the names, we get plus b theta double dot, the cosine, plus theta dot minus the sine of theta, and don't forget to multiply by the inside function, by the derivative of the inside function. Okay, so let me just write it like this: derivative of the cosine is minus the sine theta times theta dot. Okay, we're using the chain rule. We can group these two together and just get minus theta dot squared, the sine of theta, and this is 0. So what is useful about this? Is there really any use to this? There is actually. From this we can determine what x double dot is. We just take this to the other side, just changing the order, and divide by this. So we get b over 3 halves m plus the other m times theta dot squared, the sine of theta, minus theta double dot times the cosine. And we have determined x double dot. And we are actually going to need it afterwards, so I'm going to leave it here. So okay, so I just realized that I missed an m factor in some of the terms of the kinetic energy, but you shouldn't have any problems with it, don't worry, because when I edit the video, I will include this factor with the editing program. Okay, so let's just keep going. So what have we seen so far? We have seen the Lagrangian of our system, the equation of motion for the generalized coordinate x, which is this one, and well, if we're taking the derivative, we have an equivalent relation which relates x double dot to theta and theta, to theta dot and theta double dot. And well, this cannot always be done, but in this case it can, and it's actually really useful for us. Apart from that, we have also seen the equation of motion for theta, and if you don't see clearly, I have just included this m factor here and here, and here, and here, and here. And if I miss any of these factors, I will just fix it with the editing program. Okay, but well, so let's just keep going. You shouldn't worry about any of this, because when the video comes out, everything should be okay. All right, so let's just keep going. Well, yeah. So why did we express x double dot like this? Well, our idea is to get a differential equation only for theta, so we can kind of solve it and see how theta moves. Okay, how the angle changes with time. So well, let's just write it. So we have that the equation of motion for theta is mv squared theta double dot plus mv, the cosine of theta, and now comes the x double dot part. So we will just write it, our expression right here, which is 2mb over 3 capital M plus 2m, and we have these other factors: theta dot squared sine theta minus theta double dot and the cosine of theta, and this is equal to minus m gb sine theta. Okay, so this would be, let me just, this is an important relation for us later on. This would be the equation of motion for theta, and we could try to solve it, but it's I don't even know if it can be done analytically, and it could be a pain to do it. So what we usually do in these cases is to consider, well, what information can we get from our system. And one interesting information that we can get is what's called the equilibrium points. Okay, but let me just check for a minute that I wrote everything correctly, because I don't trust myself anymore. But okay, yes, and yes, I think I think that everything should be correct there. As I said, don't worry, everything will be fixed when the video comes up. So what I was saying is that we have this kind of hard or complex differential equations, or not even too complex, but whenever you include some non-linear factor, your differential equation already is, I mean, most of them cannot be solved. The immense majority of differential equations cannot actually be solved analytically. So we have to find a way around it. And the way we do it, at least in this case, in physics and in many other cases, is, well, let's see what kind of information we can get by considering an equilibrium point. Equilibrium point. And what do we mean by an equilibrium point? What we mean is, for example, let's say that initially, well, this is moving with angular velocity v, and with some velocity, linear velocity, this is x, this is y, and this is z, and here is our mass m. Let's say that initially we put our mass at an angle theta naught. Then there will be some angle for which the particle doesn't move, in the sense that this angle will stay constant. That is, if we put the particle just in the right spot, the particle will always keep moving with this angle. Okay? Of course, it will move with the disk, but the angle relative to this center of mass will always be the same. This is what we call an equilibrium point. There are actually two kinds of equilibrium points. We have a stable equilibrium, in which if you put it in equilibrium and then kind of move it a little bit, it will go back to equilibrium. And some other points are non-equilibrium points, in which if it is in equilibrium and you touch it a little bit, it will just fly out of equilibrium and never go back. So in our case, we're trying to find these equilibrium points. How do we do it? Well, just to apply what we have said that an equilibrium point is, right? So we're saying that if initially it is at theta naught, then for all t, it is going to be at theta naught. That is, it's not going to move. So this is a solution that we are trying to find. Okay, so this is what we're trying to do. If we say, okay, let's find solutions of this type. We say, okay, then theta dot is 0, and theta double dot is also 0. Then in this case, if our solution satisfies this condition, our differential equation becomes much simpler. That is, this is 0, this is 0, this is 0. So all these two terms are 0. So we get that 0 is equal to minus mgb, the sine of theta naught. And of course, assuming that mg and b are not 0, otherwise we'll get that there's no mass, or that the rod has no length. So assuming that this is not 0, we can divide by it, and we get that the sine of theta has to be 0. And this can only happen if theta naught is 0, plus some arbitrary evolution. Okay, this just means, this 2 pi k factor just means an arbitrary evolution. So if initially our particle is like this, with an angle of 0, and it moves, it will always stay there. That is, the disk will roll, and the particle will always stay like this, vertical. And this 2 pi factor just means that we're making an arbitrary evolution, right? Plus 2 pi, minus 2 pi, whatever. This is just really the same position. This is just mathematically the solution, but physically we get the same position. So our equilibrium point is theta naught equals to 0. And now we can actually do something else, which is actually really interesting. And what if we do what we said before? Let me just erase it. What if when the particle is at this state, at this position, and of course the disk is moving, what if we give it a little touch? We say, okay, the particle is not moving, it's not going to move, but what if we give it a little impulse? Then the particle, if the impulse is small enough, will kind of oscillate between the equilibrium point. Okay, we're going to go back to the equilibrium state, but it will also have small oscillation. Let's just call this oscillation E. Let's make it more general. Let's say that we're giving it every some time. It depends on time. Say, for example, now I'm not giving it any kind of perturbation, but sometimes say, let's give it a little touch. Then this perturbation will depend on time. So in general, we can consider this with condition that it is small enough. That is, it is a lot less than 1. And we don't care which side we do it. We don't care if it's positive or negative. So we're just going to impose this condition that the absolute value of it is a lot less than 1. Another way to say it would be to say that epsilon theta is around 0. It's close to 0. These are just two notations that I like to use. This is the most common one. This is like saying that it's close to 0, but we don't care the sign of it. Okay, so what I'm saying here is small perturbation. And this small perturbation is going to be epsilon of t, and we're going to say that it's close to 0. What does this mean? This means that we are going to neglect terms of higher order, in the sense that if epsilon t, I don't know, let's say that it is a small number like 0.0001, then epsilon squared is going to be all of this squared, which is going to be even smaller, closer to 0. So we are going to cut off at some point and say, okay, from these terms are too small, we're just not going to consider them, to simplify things. And in our case, we will neglect terms of epsilon squared, epsilon cubed, and so on. We will consider them that they go to 0 very fast, so we will not be dealing with them. We will neglect them. Apart from this, we will also consider that the variations in our perturbation, okay, are really small. That is that epsilon of t, how this perturbation varies with time, is also going to be very small. Meaning that epsilon naught squared and so on are also going to go to 0 very fast. So these are our two assumptions. And now that we have considered this, we can say, okay, so how do we put this into our equation? Well, let's just say that now our solution is going to be theta of t, and it's going to be our equilibrium point, right? Our particle is going to be at our equilibrium point, plus some perturbation, which depends on time. And we're going to say that it is small. But we know that theta naught is 0. We just found it later. So we also just have this. So the motion in the theta variable, in the theta generalized coordinate, is going to be this small perturbation. Okay, so if the particle is like this, it is going to be moving with epsilon t, just really, really small angles. So in this case, we can rewrite our differential equation once again. Just if you're wondering why I haven't cancelled out these m's and these b's and so on, just I wrote it like this before, and I just didn't cancel them out. But of course, you can cancel out this m with this m and this m and this kind of these b's. We'll get to the same answer at the end. So what was I saying? Well, what this means is that if theta is equal to epsilon t, then theta naught is equal to epsilon naught, and theta double naught is equal to epsilon double naught. But apart from this, we are also going to consider an approximation before we substitute, and we're going to say that the cosine of x is approximately 1 when x is very small. This comes from Taylor series, if you want to write it out here, and that the sine of x behaves like x for really, really small x. That is, just really quickly, if I have, for example, the Taylor series expansion at around 0 of the cosine, we have that this is minus 1 to the n, 2n factorial times x to the 2n, and this is just 1, 0, okay, I mean if you put 0 here you get 1, and you get 1, if you put 1 here you get a minus, you get 2 factorial, 1 over 2 factorial, and if you put 1 here you get x squared, plus so on, so on. All these terms are going to be x squared, x to the 4th, and so on, and we're going to be neglecting them. So we're going to put an approximate sign here and say that it's approximately 1. And we're going to be neglecting them because we're considering that x is pretty close to 0. If we do the same with the sign, okay, I'll just write your 0x expansion if you want to do it. Well, the sign in this case is an odd function. So we get 2n plus 1, 2n plus 1, and this, well, let's just write it. This is just 1 minus, if you put 1 here, you get 1 over 3 factorial, and you get x cubed plus so on, so on. Let me just check. Yes. Sorry, this should be an x, another one. See, I make mistakes so often, but well. And yeah, if you put a 1 here, then you get 3 factorial, x cubed, and so on. So these terms are going to be x cubed, x to the 5th power, and so on. So we are also going to be neglecting them, and we get our x. Okay, so these are our approximations. These are the conditions that we're going to be considering to solve this differential equation, which otherwise would be too hard to solve. But it's actually going to give us some nice information about this equilibrium point, which are usually very useful and very important in physics. So well, yeah, let's just substitute our epsilon naught. But before we do that, okay, let's just cancel out this m with this m and this m. So we have b squared theta double dot is just epsilon double dot plus mv, sorry, again, plus b, we got rid of this, and this. And our cosine, we said that we're going to put it as a 1, so let's just leave that 1 here. We have 2mb over 3m plus 2m, and here we have epsilon naught squared times the sine of epsilon. Oh, before I didn't say it was the cosine of epsilon, so epsilon is small, so we can approximate it as 1. Sine of epsilon minus epsilon double dot, and the cosine again we can just approximate it as 1, and this should be an epsilon. Okay? And this is equal to minus gb times epsilon. And because we have made these approximations, I am actually going to write an approximate symbol instead of an equal sign. Now, we're saying that we said that we're going to neglect terms of this kind, e dot squared. We said that right here, so we're going to say that this goes to 0. And we end up with the following relation. If we divide by b squared, well, let's just factor out the b squared, and we get 1. And this minus sign comes here, and we get 2m, b squared comes out, 3m plus 2m, and what goes here goes, well, just the epsilon double dot, and this is equal to minus gb epsilon. Now, if we divide all of it, assuming that this is not 0, okay, for example, you can assume it by saying that m is a lot larger than 2m, then 2m over 3m plus 2m is not going to be 1, but what? Assuming that this is not 0, as we said before, we can divide by it, and we will get that epsilon double dot is just minus gb over b squared, and this term right here. which I have not written here because we can actually simplify it. This one becomes just 3m plus 2m minus 2m, these two cancel out, and we get 3m plus 1 plus 2, sorry, yes, but 3m over 3m plus 2m epsilon, and this is just, well, these two cancel out, this comes on top, and it is 3m plus 2m g over 3 capital MB with this minus sign and this epsilon. And in case you haven't noticed it, this is something that we have written on this side of the word and we talked about in the beginning, but I'm going to write it a bit more clearly here so you can see it. This is the double time derivative of epsilon is minus 3m plus 2m over 3m g over b epsilon. I'm going to put some parentheses in here because this is a harmonic oscillator that we have right here. Instead of x, we have to use the variable epsilon, but it doesn't really matter. What matters is the relation. So we have epsilon satisfying a harmonic oscillator. That is, it is going to oscillate like a harmonic oscillator. This is going to be the movement around the equilibrium point for small enough perturbations. And what we can do from here is, of course, we can solve the equation. We know that the solutions are just of the form a cosine omega t, and this omega, I'm going to call it omega epsilon, because this angular frequency, do not get confused with the angular frequency of the disk. This is another one. This is just, as we said, as we will see, is just an angular frequency defined in terms of this. But we'll see it now. Plus b sine omega epsilon t. So this would be our solution. So they are sinusoidal expressions with angular frequency omega epsilon. But what is omega epsilon? Well, in our relation, we have that this term right here is omega squared, but we have this. So this is omega epsilon squared, which means that our angular frequency of our oscillations is just going to be the square root of 3m plus 2 over 3m g over b. Sorry? This is the angular frequency of our harmonic oscillator. What all this means is that when we have our mass in the equilibrium position and we give it a little touch, if it is small enough, it will oscillate around that point with this angular frequency. And from this angular frequency, we can actually get the period as the period of epsilon is just 2 pi over omega epsilon. Well, yeah. I think that's all for today. I hope that in the video you can see everything clearly and that it's not too much of a mess. I just wanted to keep all the equations here, but I don't think it's too messy. Try to organize it as best as I can, but if you have any recommendations about how to make the organization better and everything, just tell me in the comments or with an email. So, well, yeah, that's it for today, and we'll see you in the next video.